Bismillahirrahmanirrahim. Assalamu alaikum. Hello dear students. I hope you will be fine. My name is Engineer Manometer. I am lecturer Department of Technology, Sarhad University of Science and Information Technology, Peshawar. As I am teaching you the subject fluid mechanics, today is your lecture number 3. In lecture number 3, we will first study about atmospheric pressure. What is atmospheric pressure? It has been established since long that the air possesses some weight. Subsequently, it was also thought that the air, due to its weight, must exert some pressure on the surface of the earth. So, as we know that air possesses some weight, and due to its weight, it exerts pressure on the surface of the earth. Since the air is compressible, therefore its density is different at different heights. As we know that air is highly compressible, so its density changes with height. The density of air has also been found to vary from time to time due to changes in its temperature and humidity. Also, the density of air is changing with temperature and humidity with time, and from time to time. It is thus obvious that due to these difficulties, the atmospheric pressure, which is due to the weight of the atmosphere or air above the surface of the earth, cannot be calculated as is done in the case of liquid. So, it is clear from these difficulties that as the atmospheric pressure, which is due to the weight of the air which is due to the weight of the air above the surface of the earth, it cannot be calculated as it is done in the case of liquids. However, it is measured by the height of the column of a liquid that it can support, but we can measure it by taking a height of column of liquid which it can support. It has been observed that at sea level, the pressure exerted by the column of air of 1 square meter cross-sectional area and of the height of that and of height equal to that of the atmosphere is 103 kilonewton. So, at mean sea level, it has been observed that the pressure exerted by the column of air having a cross-sectional area of 1 square meter and height equal to that of the atmosphere is equal to 103 kilonewton. Thus, we may say that the atmospheric pressure at the mean sea level is 103 kilonewton per square meter, and from that we say that atmospheric pressure at the mean sea level is 103 kilonewton per square meter or 103 kilopascal. It can also be expressed as 10.3 meters of water in terms of equivalent water column and or 760 mm of mercury in terms of equivalent mercury column. This 103 kilonewton per square meter can also be expressed in terms of 10.3 meters of equivalent water column, while in case of mercury it can be equal to or it can be equivalent to 760 mm of mercury column. Here is the figure showing the atmosphere or weight of air on the surface of the earth or at the mean sea level. It is the column having the height equal to that of the atmosphere and the area of the cross section. This cross-sectional area has having 1 square meter. So the total air in this column will be equal to the pressure on the surface of the earth. So as we already studied that in this having column height having height equivalent to that of the atmosphere and having cross-sectional area of 1 square meter, the pressure exerted on the surface of the earth at mean sea level is 103 kilopascal. Next is gauge pressure. It is the pressure measured with the help of a pressure measuring instrument in which the atmospheric pressure is taken as datum. So gauge pressures are instruments or are pressure measuring instruments which are used to measure pressure by taking the atmospheric pressure as datum or zero. Or in other words, the atmospheric pressure on the gauge scale is marked as 0. Generally, the pressure is above the atmospheric pressure. Generally, this pressure is above the atmospheric pressure. Next is absolute pressure. It is the pressure equal to the algebraic sum of atmospheric and gauge pressure. It may be noted that if the gauge pressure is minus, as in the case of vacuums or suctions, the absolute pressure will be atmospheric pressure minus gauge pressure. So, absolute pressure is atmospheric pressure plus gauge pressure. A little consideration will show that if the pressure intensity at a point is more than the local atmospheric pressure, the difference of the two pressure is called positive gauge pressure. And however, if the pressure intensity is less than the local atmospheric pressure, the difference of these two pressure is called the negative gauge pressure or vacuum pressure. So mathematically, P absolute, which is absolute pressure, is equal to P atmospheric, which is atmospheric pressure, plus P gauge, which is P gauge pressure. So absolute pressure is equal to atmospheric pressure plus gauge pressure. Also, if the pressure intensity at a point is more than the local atmospheric pressure, then the difference of these two pressures is called positive gauge pressure, while if the pressure intensity is less than the local atmospheric pressure, then the difference of these two pressures is called negative gauge pressure or vacuum pressure. Here is the figure showing the different pressures. Here is the 0 point or vacuum, or where atmospheric pressure is 0. Up to this point, here is the atmospheric pressure. Above this atmospheric pressure, all pressure are known as gauge pressure, while below this atmospheric pressure are known as negative gauge pressure. So above the atmospheric pressure are positive gauge pressure, while below the atmospheric pressure are negative gauge pressure, and the sum of this atmospheric pressure and gauge pressure is known as absolute pressure. Next topic we have is measurement of fluid pressure. The principles on which all the pressure measuring devices are based are almost the same. However, for convenience sake, we may split up the same into the following two types. To measure the pressure, all the devices works on the same principle. However, for the sake of easiness or convenient, we split these two into the following two types. Number one, by balancing the liquid column, whose pressure is to be found out by the same or another column. These are also called tube gauges to measure the pressure. So the one is tube gauges, which is used to measure the pressure, and with the help of these tube gauges we find the pressure in the pipes by balancing the liquid columns. The second is by balancing the liquid column, whose pressure is to be found out by the spring or dead weight. These are also called mechanical gauges to measure the pressure. And the second is mechanical gauges, which is used to measure the pressure, and for that spring or dead weights are used to find the pressure. Tube gauges to measure fluid pressure. The device is used for measuring the fluid pressure by tube gauges are number 1 piezometer, number 2 manometer. These are the two instruments or devices which is used for measuring the fluid pressure. Number 1 piezometer. A piezometer tube is the simplest form of instrument used for measuring moderate pressures. It consists of a tube, one end of which is connected to the pipeline in which the pressure is required to be found out. So piezometer is the simplest form of instrument which is used for measuring pressure or moderate pressures, and in its simplest form it consists of a small tube whose one end is connected to the pipe while the other end is open to the atmosphere. The other end is open to the atmosphere, in which the liquid can rise freely without overflow. The height to which the liquid rises up in the tube gives the pressure head directly. In the case of piezometer, the end which is open to the atmosphere, and in this tube or in this end the liquid can rise freely, and up to which height the liquid rises, this will give you the pressure head directly. If the pressure of the liquid flowing in a pipe is to be found out, the piezometer tube is connected to the pipe as shown in figure 2.3. As you can see in figure 2.3, for example, in this pipe the pressure head is to be found out, so a piezometer tube which is L shape is connected to the pipe as shown in figure. While connecting the piezometer to a pipe, care should always be taken that the tube should not project inside the pipe beyond its surface. While connecting the tube to the pipe, it should be kept in mind that the tube should not enter the pipe. However, it should have only surface-to-surface contact with the pipe. All burrs and roughness near the hole must be removed, and the edge of the hole should be rounded off. As you connect the tube with the pipe, the surface should be clear and the roughness near the hole should be removed, and also the edges of the hole should be rounded off or clear off. It may be noted that piezometer tube is meant for measuring gauge pressure only, as the surface of the liquid in the tube is exposed to the atmosphere. So piezometer tube is used for measuring only gauge pressure, as the surface of the liquid is open to the atmosphere. A piezometer tube is also not suitable for measuring negative pressure, as in such a case the air will enter in the pipe through the tube. So piezometer tube is not suitable for measuring negative pressure, as in case of negative pressure the air will suck through this pipe and the air will enter into the pipe. So it is not suitable for negative pressures. Next is manometer. Strictly speaking, a manometer is an improved form of a piezometer tube. With the help of a manometer, we can measure comparatively high pressures and negative pressures also. Following are the few types of manometer. So manometer is an improved form of piezometer tube through which we can measure comparatively high pressures, also negative pressures, and some of the types of manometers are here. Number 1, simple manometer. Number 2, macromanometer or micromanometer. Number 3, differential manometer, and number 4, inverted differential manometer. So these are the different types which are used to measure the pressure, high pressure or negative pressure also. Now we will study these types one by one. So first is simple manometer. A simple manometer is a slightly improved form of a piezometer tube for measuring high as well as negative pressures. A simple manometer in its simplest form consists of a bent tube bent in U shape, one end of which is attached to the gauge point and the other is open to the atmosphere as shown in figure 2.4a and b. So here is the figure of simple manometer. In its simplest form, it consists of a U tube, a tube which is bent in U shape, and the one end is connected to the gauge point while the other end is open to the atmosphere. The liquid used in the bent tube or simple manometer is generally mercury, which is 13.6 times heavier than water. Hence, it is suitable for measuring high pressure also. So, the liquid in the bent tube here, in this bent tube, the liquid used is mercury, and the specific gravity of mercury is 13.6. So this means that mercury is 13.6 times heavier than water, as the specific gravity of water is 1. So it is suitable for measuring high pressures. Now consider a simple manometer connected to a pipe containing a light liquid under a high pressure. The high pressure in the pipe will force the heavy liquid in the left limb of the U-tube to move downward. This downward movement of the heavy liquid in the left limb will cause a corresponding rise of the heavy liquid in the right limb. Let's consider, for example, in this figure, a manometer is connected to the pipe and the liquid in the pipe exerts a pressure on the liquid in the tube, which is mercury. As a result, the liquid in the left limb will go downward, and as a result, the liquid in the right limb will move upward. The horizontal surface at which the heavy liquid and light liquid meets in the left limb is known as the common surface or datum line. Let ZZ be the datum line as shown in figure 2.4a. This is the common surface or datum line, and this is the point at which the liquid in the pipe and the liquid in the tube meets, and this is known as common surface or datum line, and let it is assumed as ZZ, or it is denoted by ZZ. Let H1 is equal to height of the light liquid in the left limb above the common surface in meters. This is the H1, height of the light liquid above the datum line. H2 is equal to height of the heavy liquid in the right limb above the common surface in meter, and this is H2, which is the height of the heavy liquid. In this case it is mercury, and it is denoted by H2. So H2 is the height above the common surface or datum line, and it is the height of the heavy liquid. H is equal to pressure in the pipe expressed in terms of head of water in meters. So H is pressure in terms of head of water in the pipe, and is denoted H is the pressure in terms of head of water in the pipe and is measured in terms of head of water in meters. S1 is equal to specific gravity of the light liquid, and S2 is equal to specific gravity of the heavy liquid. S1 is the specific gravity of the liquid which is in the pipe, while S2 is the specific gravity of the liquid which is in the tube or the heavy liquid. It will be interesting to know that pressure in the left limb and right limb above the datum line are equal. So we know that pressure in the left limb above the datum line ZZ is equal to H plus S1 into H1. the pressures in the left limb and right limb above the datum line are equal, so the pressure in the left limb is equal to H plus S1 H1. So the pressure in the left limb is pressure in the pipe, which is denoted by H, and the pressure in the right limb, the pressure in the left limb above the datum line is S1 H1. S1 is the specific gravity of the liquid which is in this tube, while H1 is the head of this liquid. Similarly, pressure in the right limb above the datum line is line ZZ is equal to S2 H2 meters of water, while pressure in the right limb above the datum line is S2, which is the specific gravity of heavy liquid into height H2. Since the pressure in both the limbs above the ZZ datum is equal, therefore equating pressure given by equation 1 and 2, as we already studied that pressure above the datum line in the left limb and right limb are equal, so we will equate equation 1 and 2 and we get H plus S1 H1 is equal to S2 H2. So H is equal to S2 H2 minus S1 H1 meters of water. So this equation will give you the pressure which is in terms of head of water in meter. Note, if a negative pressure is to be measured by a simple manometer, the same can also be measured easily as discussed below. As we already studied that manometers are used for measuring high pressure as well as negative pressure. So now we will see how the negative pressure is measured with the help of manometer. In this case, negative pressure in the pipe will suck the light liquid, which will pull up the heavy liquid in the left limb of the U-tube. This upward movement of the heavy liquid in the left limb will cause a corresponding fall of the heavy liquid in the right limb, as shown in figure 2.4b. Here is the figure B. In this case, we have a negative pressure in the pipe, so as a result, the heavy liquid in the tube is sucked by the pipe. As a result, the heavy liquid rise in the left limb and fall in the right limb. In this case, the datum line ZZ may be considered to correspond with the top level of the heavy liquid in the right column as shown in figure. In this case, the datum line will be the point up to which the heavy liquid comes down in the right limb. So from this point we will take our datum line and it is denoted by ZZ. Now the pressure in the left limb above the datum line is equal to H plus S1 H1 plus S2 H2 meters of water, while pressure in the right limb is equal to 0. So pressure in the left limb, this is the, if we cut here at center this tube, this is the left limb and this is the right limb. Pressure in the left limb is equal to pressure in the pipe plus pressure in this tube up to H1 height. So liquid in this H1 height is S1, so multiply S1 by H1 will give you the pressure up to this point from the center of the pipe, and next is S plus S2 H2, which is the heavy liquid, so multiply S2 by H2 will give you the pressure of this head, while the pressure in the right limb is 0 because there is no head of liquid, so pressure in the right limb is 0. Now equating these two equations, because we know that pressure above the datum line in the left limb and right limb are equal, so H plus S1 H1 plus S2 H2 is equal to 0, or H is equal to minus S1 H1 minus S2 H2, or that is equal to minus into S2 H2 plus S1 H1 meters of water. So this equation will give you the negative gauge pressure. We have example 2.5. A simple manometer containing mercury is used to measure the pressure of water flowing in a pipeline. We have a simple manometer and it is connected to a pipeline in which water is flowing. The mercury level in the open tube is 60 mm higher than that of the left limb. We have a mercury level of 60 mm in the left, which is higher than the left limb. If the height of the water in the left tube is 50 mm, determine the pressure in the pipe in terms of head of water. We have given that in the left limb we have a height of water in the left tube is 50 mm and the height of mercury in the right column is 60 mm, or in the right tube is 60 mm, and we have to calculate the pressure in the pipe in terms of head of water. First of all, in solution we will write the given data. Height of mercury column in the open tube, then that in the left tube H2 is equal to 60 mm, and height of water in the left tube is equal to H1 is equal to 50 mm. So H1 is equal to 50 mm is the height of water in the left tube, and H2 is equal to 60 mm is the height of mercury in the right tube. Let H is equal to pressure in the pipe in terms of head of water. We assume that H is equal to pressure in the pipe in terms of head of water. We know that pressure head in the left limb above ZZ is equal to H plus S1 H1. As if we cut this tube in the middle, this is the left limb, this is the right limb. In the left limb we have pressure in the pipe plus pressure in this tube up to 50 mm. So pressure is equal to pressure in the left limb is equal to H, which is pressure in the pipe in terms of head of water, plus S1 H1, which is pressure in this tube up to 50 mm. So putting values, we have value of S, which is water, which is 1, and this is the value of water, so specific gravity of water is 1, and also H1 is equal to 50 mm, which is also given. So we will get equation H plus 50 mm of water. Let this is equation 1. And pressure in the right limb above ZZ is equal to S2 H2. This is the right limb, and pressure is equal to pressure in this right limb is equal to S2 multiplied by H2. This is H2, while the specific gravity of liquid in this tube is S2. So multiply S2 by H2. S2 is equal to 13.6. Since we have heavy liquid mercury and its specific gravity is 13.6, multiplied by 60, we will get 816 millimeter of water. Since the pressure in both the limbs above the datum line ZZ equals, therefore equating 1 and 2, as we already know that above the datum line the pressure in the left limb and right limb are equal, so equate equation 1 and 2, we will get H plus 50 is equal to 816. Move this 50 on the other side, we will get H is equal to 816 minus 50, and that is equal to 766 mm of water. So the pressure in terms of head of water is equal to 766 mm of water. And this is the end of our today's lecture.